The homework that you just turned in, homework 4, I think that the case could probably be made that that's the hardest assignment of the semester, just from a conceptual standpoint. Like, it's just tricky to figure out, you know, putting all the pieces together. Plus, from here on out, a lot of the calculations are automated. I don't think there's a convenient way to automate all of the nodal method, but there definitely is a convenient way to automate Hardy-Cross problems. And so today what we're going to do is finish the example that we looked at last time, where I think last time what we had settled on was the flow rates through each pipe, but we hadn't yet calculated the pressure at each junction. So I'll show you how to do that. Homework 5 is available now. It's due a week from today. And the first problem in that assignment is a Hardy-Cross problem similar to our example. And then there are 2 other problems that come from the textbook that are related to water hammer and surge tanks. And so we'll be talking about these topics in class on Friday. Any announcement questions before we get back to this example from last time? Okay. Let's then go back. Hopefully you saved your work, and we did the iterations, copied and pasted, just to summarize where we were at. In the first round of calculations, we used the fully turbulent flow assumption to calculate F. And then the 2 main things that sometimes will cause mistakes or errors is, number 1, remember that if you have a common pipe, and so pipe CE is in both loop 1 and loop 2, and pipe EF is in loop 1 and loop 2. So we have to treat those 2 pipes kind of special, because our initial flow rate guess isn't what we got from that initial balance that we did on the paper. You would instead, for those pipes that have a counterpart in the other loop, you would do the opposite of the most recently calculated flow rate from the other loop. So you'll notice equals negative of that one. Same thing for EF, equals negative of the flow rate from the previous calculation, since it's a common pipe. And then another mistake that sometimes gets made here is in the delta Q, forgetting to put the minus sign in that formula, because it may not be as obvious that that needs to be done. But so we went through a couple of times. In the 4th iteration, I mean, things are mostly stabilized in the 3rd iteration, but since this is such a low flow rate pipe, there's not much flow going through it. And so the percent change looks kind of unnaturally big, because the delta Q compared to the low flow rate, you know, if this percent change is essentially the delta Q divided by the corrected Q, then it just appears big because the flow rates are so small. The denominator in that fraction is low. So one more iteration, and then all the percent changes are, we'll call this good enough, 1%. Now that we know the flow rate through each pipe, let's calculate the head loss through each pipe. And back to this idea from here, that head loss is the R value times the flow rate squared in our case, because we're just using the Darcy-Weisbach equation. And so the R value is, when we write the Darcy-Weisbach equation in the form H sub F is F LQ squared divided by D2G A squared, then if we take all of this, that is R. And so H sub F is R times Q squared. So it's just going to be the R values that we have here. So head loss through each pipe, it's equal to R times Q to the power of N. So that's going to be the head loss through each pipe. And we can drag it down and find the head loss through all of the pipes. So let's look at where is there a lot of head loss and where is there very little. You'll notice through pipe BC, there's virtually no head loss through that pipe. And we can see some if we expand the numbers out more, but there's very little head loss because there's very little flow rate through pipe BC. There's a lot of head loss through pipe AF, and that is because the flow rate is relatively high and the resistance is also relatively high. So there's lots of flow going through pipe AF, so that's this one. And since there's a lot of flow going through there, but it's a relatively small pipe, you know, the diameter is just 0.4, so there's a lot of resistance because of that small diameter. So there's a big head loss through that. So we know the head loss through all of these pipes. Now in the initial sketch that we had, it said that the pressure at A is known to be 600 kilopascals. That's kind of a control point, as it's called. So it's a location where we know the pressure and we want to find out what is the pressure at each of these other junctions. Now, assuming that they all have the same elevation, that the only thing that's causing a pressure change is the head loss through the pipes. So we can calculate the head at each of the junctions, and at A, the head is the pressure, 600 kilopascals divided by unit weight, 9.81 kilonewtons per cubic meter. So there are 61.162 meters of head at junction A. Now I've written here the direction and magnitude of all the final flow rates that I calculated in my last iteration. Now, some of you had different initial flow rates from me. Did you finalize your spreadsheet and make corrections where necessary? I'm curious to know, did we all end up with about the same flow rates regardless of what our initial guesses were? Yes? Yes. Okay. So your flow rate should be the same as this. So at B, is the head at B higher or lower than the head at A? If the water's going from A towards B, it has to be lower. The water wouldn't be going from A towards B if there was more head at B. So the water always flows from high head towards the low head direction. And so what I've written here in the margin is that the head at B is the head at A and then minus the loss through that pipe. And I just calculated the loss through the pipe. So I want to find the loss through pipe AB. And so pipe AB was this one. So you can see here's pipe AB, and based on the flow rate through that, here's the head loss. And so the head loss tells me that if there was 61.1 meters of head at A, then the head at B is just going to be the head at A minus the loss between the two pipes. And then we follow the same process for junction C, except for that since we're going opposite flow, the head will be higher. So the head at junction C is the head at C is the head at B plus the head loss through the pipe, because we're going against the flow direction, and if you're going against the flow direction, that means that the pressure and the head is going to be higher at junction C. So plus the head loss through BC. So here is the head loss through BC. It's pretty minuscule. Okay, so that gives me now the head at junction C. Okay, now the head at D. So the head at D is going to be the same as the head at C plus the losses through the pipe. Now, does everybody understand why sometimes I'm adding the pressure, why sometimes I'm adding the losses and sometimes subtracting? It all depends on the flow direction. And so, for instance, the reason why I subtracted the head loss to go from A to B was that from A to B is in the direction of flow. So you see the arrow is saying that the water goes from A towards B. And so the energy at B has to be lower than the energy at A. But now, like in the case of location D, the head at D is however much head there was at C plus the loss through the pipe, because I'm going against the flow direction. So that must mean that there's more head at junction D. So now I want to add in the losses through pipe CD. Okay. Junction E is going to be less head than there was at C. So I'm starting with the head at C and subtracting the losses that went through pipe CE. So here's the CE losses. And then the last junction is going to be F. And so F is however much energy there was at E. And now I'm going to add, because it's opposite the flow direction, so plus, and it is plus the loss through pipe EF, so plus that. 56.394. Now, we've got the head at each of the junctions. Let's just double check junction F, because I got to junction F by starting at the head at A and finding the head at B, then C, then E, and finally F. The other way I could find the head at F is just going directly from A towards F. So as a check, let's say the head at A minus the losses through AF. So here's the losses through AF, and 56.394 is the same as if I calculated the head through this more circuitous indirect route. All right, so we've got the pressure, excuse me, the head at each junction, and now the pressure is simply going to be the head at that location divided by 9.81, and that'll give us the pressure at kilopascals. No, I'm sorry, multiply. Yeah, pressure is head multiplied by gamma, and so 600 kilopascals, which is what I kind of already knew about junction A, but now I also have the pressure at each of the other junctions as well. Any questions about that? What would we do? Now, these calculations assumed that all of the elevations were the same at A, B, C, D, and so on. Do you have a question?
For your junction A, how did you determine that to be 61?
The given pressure from the diagram is 600 kilopascals, and head, H, comes from the V squared divided by 2G. It comes from the elevation, and it comes from pressure divided by gamma. So when we say head, we mean those three places that the energy can be. So if we just assume that velocity head is negligible, and that all of these are on the same elevation, then the head is, all of the head is going to come from the pressure. And so it's just going to be the 600 kPa divided by the unit weight. So if you were given elevations for A, B, C, D, then the pressure wouldn't just be as easy as multiplying the head by the unit weight. If there's different elevations, then you'd need to, with the total head, subtract out the elevation and then find out how much head is left after the elevation change to give you the pressure at that location. And in fact, that's what you're going to have to do on the homework assignment. If I can just give you a quick preview of that. here is the problem from the homework assignment. You're working in traditional units, so be aware of that any place G is going to be in the equation, you'll need to switch over to 32.2. But maybe more importantly, here we have 3 loops. In the homework, in the illustration we just did, there were only 2 loops. Now the process is the same, but it's just that you have some additional common pipes. And so, if this is loop 1, and that's loop 2, and this is loop 3, you need to be sensitive to the fact that some of these pipes are going to be also in the other loops. But what I was just mentioning about finding the pressure at each junction, you have the pipe characteristics, the inflows and the outflows, and so the first thing you'll do in the homework is splitting up the flow. That manually where you're writing on the paper to figure out the 3 cubic feet per second, a certain amount is going to go that way, a certain amount is going to go this way, and then here a certain amount is going to come from one direction, a certain amount is going to go from the other. So you'll figure out the initial guess of flow through each pipe, do that spreadsheet process, but then in the end, when you calculate the head at each location, like this, then the pressure is also going to have to take into account the elevation differences at each location. And so the pressure at, I think I tell you, it must not have copied over from the assignment itself, I think, tells you the pressure at A. I'll have to double check to make sure, but I'm pretty sure I gave you a control point of a known pressure at A, so that you'll find the pressure at D. It's going to be partly based on the head loss and partly based on the elevation change. So you'll notice, for example, the elevation at location A is 482.65. So if there was 0 flow, if it was just static conditions, we'd expect that the pressure at B would be higher because the elevation is lower. So it's like you're downhill from A to B. The elevation is lower, so the pressure should be higher because of that, but there's also head losses through the pipe. So it's the combined effect of the delta Z and the head loss through the pipe that will allow you to estimate the pressure at junction B. So I think this problem will probably, I bet there's people here who will solve it in half an hour, maybe less. But if you make a mistake and can't find what is the error, then it's the sort of thing where you could spend 4 or 5 hours. So I suggest if you get started early, then that gives you plenty of time to have someone else with a fresh set of eyes. I'll look at your spreadsheet if it's not converging or if your F values aren't getting repeatable. I sometimes can find the mistakes, and so give yourself an early start and then you won't be stuck overnight trying to find the mistake yourself. All right, so that's the first problem in the assignment. Any questions on the Hardy-Cross method before we move on? All right. So the other thing we're going to do today is practice the Hazen-Williams equation. I have a handout for you with 2 problems. One is in the traditional units, one is in SI units, and we're going to try and calculate, using the Hazen-Williams equation, what is the pressure at one location for the second problem, and for the first, what flow rate would apply when we have a known pressure difference. So the reason why we're doing this is I don't want us getting like really technical and in the weeds on these spreadsheets. I don't want you to lose focus on the more basic, like quick problem solving methods that you've learned before. So we'll occasionally like revisit the Hazen-Williams equation because it's kind of the easiest way to do a quick and dirty calculation for hydraulics, and it's also the thing that you're most likely to see on the FE exam. So we'll both learn like the real engineering applied stuff for your career, and then kind of the teach to the tests type stuff is preparing these Hazen-Williams problems. Okay, on the first problem, I've drawn a sketch here on the whiteboard that just shows a horizontal pipe. The water's flowing from 1 to 2. Since it's horizontal, Z1 and Z2 are equal. Since it's just flow through a pipe and the diameter isn't changing, then the two velocities are going to be the same. It's not that the velocity is 0, it's that V1 and V2 are equal. And so what that enables us to do is cross out the velocity term from the energy equation on both sides. It allows us to cross out the elevation term on both sides of the energy equation. And so then H sub F is just going to be the delta P divided by gamma. So we can calculate the head loss between 1 and 2 by the measured pressure difference divided by the unit weight of water. So having H sub F, here in the equation, it's asking for S sub F, not H sub F. And so H sub F has units of meters. So it's the head loss. S sub F, remember, is the variable for the slope of the energy grade line. And so it is the H sub F divided by the length of the pipe. So H sub F divided by L, and we know here that this pressure measurement was taken 75 meters apart. So from the measured head loss and the given pipe length, you can get S sub F and then calculate the flow through the pipe in terms of its velocity, multiply velocity by area, and that will give you the flow rate.
Like when you back calculate it? Yeah. Yeah, because, I mean, essentially what's happening is you are, these factors are 1.5 and 0.54.
There you go. Okay, now we're not thinking about it.
They're not exactly what they're taking it to more digits, and so anytime you have taken something to an exponent, right? It's going to
No, you don't.
If you look on a percentage basis, 128 versus 0.2, that's only 3%.
Yeah.
So the 6.82 times this whole expression can be solved without using the direct. So what I went ahead and did is I divided this by when you like it's confusing.
Something off by that, that little bit. He'd explain that quite a ring.
Okay. We'll start there.
She got his.
148. I got you.
We're talking about next week.
Okay, on problem 1, the handout I gave you had 2 equations on it. And these are the 2 equations that were given, since it was in SI units. Now, both of these are the Hazen-Williams equation. It's just that one of them has been rearranged to solve for the velocity if you know the head loss situation. And that's what we had. We had a measured pressure difference, which defines the H sub F, and H sub F over some length gives you S sub F. And so I think it's simplest to use this top equation, but you could also use the bottom one, where if you know H sub F, then you're solving for V. These two are equivalent, and so you can get the right answer either way. And I think that's what Elizabeth did. You calculated at both approaches, right? All right. So on the second problem, by the way, so here's the solution to the first one. Any questions about that first problem? The method that was used here? All right, on the second one, water's flowing through a cast iron pipe. The elevations aren't the same this time, and so we can't make the same assumptions that we did in the first problem, that Z1 and Z2 are equal. There is going to be an elevation difference when you put it into the energy equation. We're trying to solve for the unknown pressure downstream. And so how would you know which formula to use of the 2 that I gave? Well, you already know the velocity. So since you're not solving for the velocity, but you are trying to find out the pressure downstream, and that's based on the head loss, my suggestion is to use the top of those two equations. Use the bottom of the two equations, because we already have V. We're trying to find H sub F. So of the two, using this formula to calculate the H sub F and then substitute it back into the energy equation. Here's the solution to the second one. So you find the pressure in terms of pounds per square foot. And then, let's see. So the head loss through the pipe is 39.8 feet. Substitute that back into the energy equation to solve for P2. It should be 62.9 psi.